Hello friends, my name is Tushar and today I'm going to talk about how to design a chat or a messaging service. This is my third design video. If you have not watched my other two videos, I highly recommend watching them. Starting with a disclaimer, design is a very subjective and broad topic. Whatever I'm going to teach here is just based off my personal experience and talking to friends and peers. I have no idea how this company is implemented. So just take it with a grain of salt and do your own research. So let's start with the subtle difference between Facebook Messenger versus something like WhatsApp or Signal. I'm sure all of you must have used one or both of these services. So with Facebook Messenger, what they do is they keep all the data in the messaging service. Whatever you chat, they keep all that information in their service, in their system forever until you go ahead and delete them. And WhatsApp or Signal, what they do is as soon as the other party receives the message, they just delete the message. So they only keep the message as long as the other party has not received the message. One more subtle difference is that with the Facebook Messenger, if Facebook wanted, they could read those messages unless you turn on end-to-end encryption. While WhatsApp or Signal has end-to-end encryption, which means that the middle tier or the services in between cannot read your messages. So what we are going to design today is more like Facebook Messenger and less like WhatsApp or Signal. So these are some of the features or topics we are going to talk today. One-on-one chatting, how the other person is going to receive your messages. We need ability to show that the other person is online and when the message is sent and when the message is read by the other party. We need capability to send pictures or other big files. And then I'm going to talk about how the database could be designed and also talk a little bit about security. Security is a very hot topic, so I'm just going to talk some bits and pieces, but overall my design is going to be very weak on the security and hopefully you can do more research on your own. So next, let's deep dive on these topics. This is the further breakup of the service. If you have watched my previous videos on design, this must be fairly familiar to you. So here we have a user A and he talks to the load balancer. Load balancer can operate at level 3, level 4 or level 7. Load balancer talks to one of the nodes behind him, N1, N2 and N3. Most of the time they are stateless and what they do is they do bulk of the work, which is doing serving requests for the user, talking to the database, talking to the distributed cache. You're going to have a database. I'm going to use Cassandra, which is my favorite database, but you could use anything, any other database. And for distributed cache, we're going to use Redis, which is going to store temporary information for the user. So next, let's talk about what happens when the user logs in for the first time into Facebook. Let's first talk about HTTP architecture. HTTP is a request-response architecture where client sends a request and server sends a response back. Thing to notice here is that server cannot initiate the request to the client. So what that means is that that does not work very well with the chat application. Why? Because if user B has some data to send to user A, and so it sends the data to the server, and the server cannot initiate a request to the client because that's not how HTTP works. To work around that, we have a few alternatives, and I have listed some of them here. The first one is a WebSocket, which is fully bidirectional connection. What that means is once user A is connected to the server, both server and client can initiate the request because it's bidirectional. The second one is BOSH, which is bidirectional stream over synchronous HTTP. What it does is it works over HTTP, and what it does is user A or client sends a request to the server and server holds on to that request till certain time has passed or till he has some new data, at which point he will send a response back, and then user A will instantly initiate a new connection to the server, a new request to the server. So that way, if server has some new data, he can send a response back, at which point user A will again start a new request. And the third one is long polling over HTTP. where client sends a HTTP request to the server, and if server has some new information, he responds with that information, or he says that I do not have any information, and then the client waits a certain interval of time and then starts a new request. So of all the three, WebSocket works the best for our scenario. One more thing with the WebSocket is that it has something like sticky session, where if a user A starts a request to the server, and if that request went to N1, then it's always N1 which is staying in connection with user A. So all the requests from user A will always end up at N1, and you will see how we're going to use that to our advantage in this design. So next, let's go deeper into our messaging app. You go to a browser, you type in your Facebook credentials, Facebook authenticates that. How that works is outside the scope of this video. Once Facebook authenticates you, it knows that you're ready to send and receive message, and also the fact that you're online. So let's see what happens here. So user A goes to a load balancer. Load balancer will pick one of the hosts behind him based on FIFO or number of connections, or just based off the load average on this host. So let's say load balancer picks N2. Remember, this is a WebSocket connection, so it's bidirectional in nature. So both server and client can initiate a request. So at this point, while user A is not sending any data, they're just hard beating between them. So N2 is managing user A. Why we need to constantly heartbeat? Because that way the server knows that user A is still there, and also user A knows that this particular server is still there. So this heartbeat information is going to be stored in Redis. So in Redis we're going to store user A. So for user we're going to store user A, and then we're going to store N2, which server is managing him, and then we're going to store when was the last time this heartbeat was received. So it could be like November 17th, 5:10 p.m. and 03 minute, and then some millisecond. So at this time, the last heartbeat was received, and every time N2 gets a new heartbeat from user A, he's just going to go and update that into Redis. So let's talk about our decision to use Redis here. So Redis is a distributed cache. It holds all data in memory, and if you want, you can also flush that data into hard drive. And it's also master slave, so slaves can hold same copies as master. And there could be some discrepancy between them, but most of the time slave has pretty much all the information which master does. So can we hold all this data in memory? So Facebook has what, like 1 billion users, and every host these days can easily have like 100 gigabytes of memory. So holding 1 billion users information, it would not take more than 10 hosts to hold such kind of information. So we can easily hold all that information, all this information for all 1 billion users in memory. By keeping the information in memory, we have multiple advantages. First, when N2 writes here, that write is super fast. And also, if someone else needs to read that information about user A, then they can do it very quickly. So that's why we're going to use Redis, which is going to hold all the information in memory. So coming back here, our user A and N2 is constantly hard beating back and forth. Let's talk about a scenario where N2 dies down. I mean, this is very easily possible, where N2 dies, the guy who was managing user A. So what will happen in that case is that if N2 dies, user A, this WebSocket connection will instantly break. User A will know that and the other end of the server died. So what he's going to do is he's going to initiate a new connection with a new host, and in this case it could be N3, and what N3 is going to do is he's going to start updating this heartbeat information here. So in this Redis we're going to replace user A, N3, and then the last time this heartbeat information was received by N3. So N2 dying is not a big deal. Someone else will start taking his responsibility and will start updating Redis. Another thing is that if user A dies or is inactive and he stops heartbeating with N2, then N2 will stop updating the heartbeat information here, which means that other users can see this information to use this information to see that when was this user online the last time. So if you know on Facebook, it shows that these users are online and this user was online like 45 minutes ago, 1 hour ago. All that information can be retrieved from this Redis cache, where we can say that if user A is online or not based on last time the heartbeat happened. So now we have this constant heartbeat going on. Next, let's talk about what happens when we actually want to send a chat message to another party who is online right now. Let's suppose there is a user B who is friends of user A, and he is also online right now and is constantly heartbeating with N3. So N3 has stored this entry in Redis for user B. User B, N3 that he's managing user B, and this is the last time it heartbeated, and let's assume that this time is fairly recent. Now user A wants to send message to user B. So what user A is going to do is he has his connection open with N2, so he's going to send this message to N2. So let's say he sends hi. So hi goes all the way to N2. Now N2 will first persist this message in the Cassandra database, and we are going to look into more details later on. So first he persists that message in Cassandra database, then he's going to check that is there anyone who is managing user B. So when user A sent hi, he also said that who he wants to send this message to. So in this case, hi to user A, so to user B. Then N2 will look into this Redis to see who is user B online, and if he's online, who is managing user B. So he'll come here, he'll see that N3 is managing user B, and he was online very recently. So what N2 will do is he will send this hi to N3 and fact that you need to send this to user B. N2 will not initiate a direct connection with user B. Why? Because N3 already has this WebSocket open, so why spend another connection? So he just sends this message to N3, and then N3 will then send this message back to user B, and user B will send this will instantly see this message. So this is the flow of what happens when both user A and user B is online. Obviously we skipped some of the Cassandra aspects, and I'm going to talk about that. So next, let's see what happens when user A wants to send message to user C and user C is not online. In this case, user A sends message hello to N2, then N2 will look into this Redis and there is no entry for user C. That tells us that user C is offline and no one is managing that. In that case, N2 will just persist this message hello into the database, and will also persist the fact that there are some unread messages also in the database. And when user C does come online, and whoever is managing user C, let's suppose N1, he will read from the database, see that there are some unread messages, and then he's going to transmit all that information to user C, and at the same time he'll update his Redis entries, updating the fact that user C is online. So this is our big picture of how the chat communication will happen between two users. Next, let's talk about how our database schema will look like and how we are going to handle some of the security. These are the three bare minimum database tables which we will require to run this chat service. So first, let's look at user table. So there is user 1, user 2, conversation ID, and encryption key. So here, when user A becomes friends with user B, then we are going to put an entry into this user table saying user A, user B, their conversation ID. It will be a unique generated number, and encryption key, which will also be a randomly generated encryption key. But while it is stored here, it will be encrypted with another master key, which Facebook will store somewhere else. Now, remember, encryption is a very hot topic, or security is a very hot topic. So what I'm describing here is a bare minimum, and what Facebook would be doing is way more complicated. Now, user A logs in. When user A logs in, we know that who his friends are and pull all the information about his friends related to his chat into the device. So let's suppose user A only has one friend, user B. So we're going to pull user B, his conversation ID, and the decrypted version of this encryption key. So N2 will pull all that information and then send it across to user A. So user A has all this information, And now if he wants, he can chat with user B. So user B also came online, and he also pulled in all this information from the same table, and he also has this conversation ID 5 and the decrypted version of this encryption key for specifically chatting with user A. So now when user A wants to send a message to user B, first thing he does is he encrypts the message on the device itself with this encryption key. Then he sends this encrypted message to N2. What N2 does, and he also sends this conversation ID and the fact that he's sending message to user B. What N2 does is it first persists this information into the database. So here in this conversation table, so we have this conversation ID, which is like a foreign key here. Then we'll have some time T1, and T1 also has to be uniquely generated time. To do that, we can take the current milliseconds and apply some and add some random bits at the end of it. Then we have this text which is in encrypted format. So I'm going to write it in a curly braces indicating the fact that it's encrypted. So we have this encrypted hi, and there's a URL which we're going to talk about later on. So we have, so first N2 persists all this information in conversation table. Then he's going to check that is there anyone else, is there anyone else who is managing user B, because that's where this message is destined to. So we see that N3 from that Redis table, we see that N3 is managing user B. So we send this encrypted hi to N3, and N3 will send this message to user B. And what user B is going to do is he already has this decryption key. So he's just going to use that key to decrypt this message, and he will get hi here. One other thing I forgot to mention was that each of these nodes can manage hundreds or potentially thousands of sessions. So it's not like N2 is just talking to user A. N2 could potentially be talking to tons of such users. So coming back here, so this way when user A sent hi, the user B found this message. And if user B wants to send a response to that, say hello, then again the reverse of this is going to happen. He already has this information, so he encrypts hello with this encryption key, sends it out to N3 with the conversation ID and the fact that it's going to user A. N3 will first persist that information in conversation table, so 5, and say T2, again T1 and T2 will be unique, and then hello, and then he's going to first persist that, then he's going to say who is managing N2, so who is managing user A, so N2 is managing user A. Then he's going to send this message to user N2, send this hello encrypted version of hello to N2, and he's going to send it back to user A. And user A also has the same key, so he's going to decrypt that message, hello, and he's going to read it here. So this way, a basic flow will happen with the help of these tables. Next, let's see what happens when you send a message to an offline user. Let's suppose user A wants to send a message to user C who is offline right now. So just like before, when user A logged in, he can fetch all the information about user B and user C, which is a conversation ID and their encryption key. Now user A wants to send a message to user C. Let's suppose that message is hello. So first he will encrypt hello with the user C's encryption key, and then he's going to send this information to N2 along with the fact that it's going to go to user C, and then conversation ID is 6. N2 will first insert this entry into the conversation table. So here we'll insert 6, and that's a time T5, and then encrypted version of hello. And from user is which user it's coming from, so in this case user A. Now, as soon as this entry is written into the conversation table, we know that the message is safe. At that point, N2 can confirm to user A that the message is sent. We don't know that user C has still not read the message, so we do not say read, but we have sent the confirmation to user A that the message is sent, and that confirmation is sent by N2. Now N2 will look into the Redis to see that is user C online right now, and is there any host which is managing user C. Since user C is offline right now, he cannot send this message to user C. So what he's going to do is store this message in this unread table. So to user in this case is user C, from user is user A, and time is T5. Time is saying that the time of the earliest unread message. Now let's suppose that user C comes online after say 5 hours. So as soon as user C comes online, first he's going to fetch all this information. Basically, what is the conversation ID and what is the encryption key for user A. So user C fetches all that information, and also he's hard beating with some server, say N1. So remember, this is a bidirectional connection. So he's talking back and forth with N1, and N1 was the one who fetched all this information for him and sent it to user C. And also N1 is now updating the Redis, indicating that user C is online. So other users like user A, who is a friend of user C, would now know that user C is online. Why? Because N2 is constantly looking into the Redis to see if friends of user A, which friends of user A are online. And as soon as user C comes online, N1 updates that into Redis, and N2 reads that. So he knows that user C is online, so he's going to notify that information to user A. Now now user C, as soon as it comes online, he wants to see if there are unread messages. So N1 is going to do that for him. So N1 is going to look into this unread table. He's going to see that there is a user C, user A, and at time T5, there is some message since T5. So he's going to look, he already knows the conversation ID between user A and user C, which is 6. He'll look into this thing, he'll get this, pull this information and send this encrypted version to user C. So he gets encrypted hello, and user C already has the encryption key, so he's going to decrypt this message and he's going to see hello. As soon as he gets the hello, at that point, user C, we know that user C has read the message. So he's going to confirm to N1 that, hey, I read the message. N1 now knows that the message which was sent from user A has been read. So then he's going to see that, hey, is user A still online? If he's online, let's notify him. So he's looking to the Redis. Let's suppose user A is still online, and then he'll see which host is responsible for that. So that's N2. So he's going to tell N2 that, hey, tell your user A that user C has read this message, and N2 will do that. He'll tell user A that user C has read this message. And as soon as that happens, we will remove this entry from the unread table. On the other hand, if user A was offline, then N1 will just put an entry into a read table saying that message from user A to user C at time T5 has been read. So when user A comes online, N2 will read into the read table, see that user C has read this message, and notify him that his message till point T5 has been read by user C. So as you can see, we cover all the 3 use cases: the fact that how to know that the other person is online, how do we know that the message has been sent, and how do we know that the message has been read. So this is my basic architecture for how a basic chat service could be designed. Obviously, there are a lot of race conditions here, but I think this is a good initial design from on which you can build on more and add more features. So next, let's talk about how do we handle the case where user A wants to send a picture to user B. Now user A takes a picture on his device and he wants to send that picture to user B using Messenger. So first, what the device would do is, it already has this information about user B, which is conversation ID and the encryption key. First, it will encrypt that picture with this encryption key, then send this message to N2. So N2 will receive the picture in the encrypted format, the conversation ID, and the fact that it needs to be sent to user B. Then N2 knows that it's a picture, not a text message, so it's going to talk to the blob storage. Every company has a blob storage, so I'm sure Facebook does too. So N2 will talk to this blob storage and it'll store this picture and get a corresponding URL back. So this picture is stored in the blob storage in an encrypted format, which is encrypted with this key. So N2 gets a URL back. Then first he's going to store this entry into our user table. So here he'll store the fact that it's related to conversation ID 5. Then sometime say T4. And now we don't have any text message, but instead we have a URL. So let's call it URL1. So let's suppose we got a URL1 back. So we're going to store URL1 in this URL. And then N2 will check that is user B online, and he is online because he's hard beating with N3. So N2 will send this URL and a thumbnail of this picture to N3, and N3 will send them back to user B. So original picture could be 5 megabytes, but the thumbnail could just be 5 kilobytes. So we'll send that thumbnail picture to user B along with this URL, and if user B is interested, he can click on the picture, and then we will take this URL and download the entire picture. So N3 will take this URL and download the entire picture for user B, and then user B can decrypt that picture with the help of his encryption key. So this is one of the way you can transfer a picture, or you can send a picture from user A to user B, and this could also be used to send like some other files, zips, or whatever other big files. So next, let's talk about what are some of the optimizations you can do in persisting the data, and also how you could potentially do a basic search on the conversations. Let's again look at this conversation table. One thing I forgot to mention is we also need to store the from user so that we know that which is the sender of who is the sender of the message and who is the receiver of the message. Now if you look at these messages, you see that something happened at T1, something happened at T2, something happened at T3. So once a message is inserted, they are immutable. We just keep adding more messages here. We do not update the existing message. So to optimize the storage, what we can do is we can take last few days of data, convert that into one blob structure, and store that in a blob storage instead of storing it here. Now you would ask, why would we want to do that? Because storing something in a blob structure is way more cost efficient than storing them in this format here. So what I would do is, let's say today we are in this time T6 and we have conversation ID and blah blah. So what we're going to do is take data except yesterday, so let's say yesterday's and before data, combine them into one blob structure, take that and store it here, get the URL back, and replace that with that URL. So here we'll store 5, let's say the earliest time of that blob, so T1, and instead of all this, we'll just store that URL1. So for the current messages, keep them in the text format. For the older messages, keep them in the blob storage. So when you go back and look into history, you would have noticed how slow it is. That's because I think they must be doing some of this optimization where they might be storing it in a blob or some sort of an archive. So when you go back and look into the older chat, it will pull you that information, but it will be a little slow. So in this case, he'll go and fetch this. If you're looking for the older data, he'll go and fetch on this URL, download the blob storage, and then send it to you, and then you can decrypt it using your decryption key, using your encryption key. Okay, so this is our optimization, our little optimization for storing the data. Next, let's talk about search. So for search, I think the easiest thing would be to just search through the text anytime someone does a search. You could also build some sort of a reverse index, but I think it would be very cost prohibitive to build a reverse index. Instead, since the search is done so rarely on your chat history, that service might be better off just searching it directly in the text messages when someone does the search. The last thing I wanted to talk about was group chat, and I did not mention that at all before. So for group chat, I think this architecture can easily be used for the group chat. So remember, we had a user table. Along with that, we can also have a group table which shows the group membership, and then they can have a conversation ID, and that conversation ID can again be stored here, and all the same things would apply in this architecture and then all the same things would apply as we discussed before. So this is all I have to talk about. How would you design a chat or a messaging service? So I would like to hear your comments, or what you think about this video, or also how you would have designed this video. So thanks for watching this video.